All right, welcome to your mandatory induction as a trainee technician. In this explainer, we're going to take you from the absolute basics of component theory right up to the fine art of precision calibration. You're going to want to pay close attention because this stuff is the foundation for everything you'll do here.
And let's be absolutely clear about the stakes right from the get-go. This isn't some academic exercise where you can get away with a small mistake. In our world, a calculation error isn't a bad grade, it's a malfunction. The report you're about to produce, well, that's your official certification of competency because patient safety literally depends on your precision.
Okay, before you even think about touching a circuit board, you have to be fluent in the language and the laws of electrical circuits. This is your essential toolkit.
Think of these as the alphabet of electronics. These are the International Electrotechnical Commission's standard symbols for, well, everything, from a cell to a capacitor to a thermistor. There's zero room for interpretation here. You have to reproduce these with absolute precision in all your schematics. Ambiguity is your enemy.
First up is current, which we measure in amperes. You know, the easiest way to wrap your head around this is to think of it like the volume of water flowing through a pipe. It's just the amount of charge that's zipping past a certain point every second. Next up, potential difference, or as you probably know it, voltage. So if the current is the water, voltage is the pressure that's pushing that water through the pipe. It's the energy that gets the whole show on the road.
And finally, resistance, measured in ohms. This is the last piece of our little analogy. Resistance is basically how narrow that pipe is, restricting the flow. The higher the resistance, the tougher it is for that current to push through. Simple, right?
So now that we have the alphabet, the symbols, and the units, it's time to learn the grammar that connects it all. These are the fundamental laws, things like Ohm's law and Kirchhoff's rules. All they're really saying is that energy and charge are conserved. What goes into a circuit has to come out. These laws govern every single circuit you will ever build. Period.
Okay, those laws are universal, for sure, but they have to work through physical things, through components. And that's why your choice of materials is the first, and I mean the first, critical decision you'll make in any design. And it's a choice based completely on the physics of the material itself. Take a look. On the left, you've got a conductor, like copper. See that orderly atomic structure? It lets electrons just flow right through, which is exactly what you want for transmitting a signal without losing anything. But on the right, you have an insulator, like rubber. It's got this chaotic structure that traps electrons, which is perfect for safety, to protect the user from getting a shock. Now, this is where things get really interesting. A component's behavior isn't always constant. A standard fixed resistor, it follows Ohm's law perfectly, giving us that nice, straight, linear graph. But look at the filament lamp. As it gets hot, its atoms start vibrating like crazy, making it way harder for electrons to get through. So its resistance actually goes up, creating that classic nonlinear curve.
Theory is great, but now it's time to get our hands dirty in the lab. We're going to walk through 4 standard operating procedures, or SOPs, that you'll be documenting in your report.
Your first mission is SOP1, linearity testing. You're going to build a simple series circuit, slowly crank up the voltage, and carefully record the current. This is exactly how you'll get the data you need to plot those ohmic and non-ohmic graphs we were just looking at.
All right, moving on to SOP2. We're exploring circuit topology. You'll build 2 fundamental setups, a series circuit where there's only one single path for the current, and a parallel circuit which gives the current multiple paths to choose from. The whole point here is to measure and really understand how voltage and current behave totally differently in each configuration.
And this chart just spells it out beautifully. In a series circuit, every resistor is just another roadblock, so the resistances just add up, making for a big total resistance. But in parallel, adding more resistors actually creates more highways for the current to take, which, get this, reduces the overall resistance. It's a super important and kind of counterintuitive concept to get down cold.
Next up, SOP3, signal filtering. Now, in medical devices like an ECG machine, a clean, stable signal is absolutely non-negotiable, and capacitors are the heroes here. They act like these tiny little reservoirs of charge, absorbing spikes and filling in the dips to smooth out noisy signals and filter out all that unwanted high-frequency junk.
So listen up, because this is the crucial point. The math for combining capacitors is the exact inverse of the math for resistors. In parallel, you just add them up. Easy. In series, you have to use that inverse rule.
Do not get these mixed up. It's a really common mistake, and it will completely wreck your calculations and your circuit.
And for our final procedure, the potential divider, this is where it all comes together. Your mission, should you choose to accept it, is to take a 6-volt source and, by picking just the right resistors, slice that voltage up into smaller, precise outputs. This is hands down one of the most useful circuits in all of electronics.
Excellent. You've built the circuits, but guess what? You're only halfway done. The most important step for any technician is verification and quality control. This is the final audit.
Your workflow needs to become this constant loop, almost like a mantra. First, you predict the output using the formula. Then you measure the actual output with a multimeter. And finally, you audit your results by comparing the two. Your report absolutely has to include this comparison to prove the circuit's integrity.
Now, even if you do everything perfectly, your measured values will probably never match your theoretical predictions exactly. Don't panic. This isn't failure. It's just reality. Your job is to identify and document these sources of error, things like component tolerance, the limited resolution of your tools, and even how heat can change resistance while you're measuring.
So how do we shrink that gap between theory and reality, especially when a life could be on the line? Well, the answer is to tighten our control. We improve accuracy by using better equipment and better components. We move to high-precision multimeters that can see those tiny fluctuations, and we use low-tolerance resistors that perform much closer to how they're supposed to.
And this is it, your final submission checklist. Every single item here, from your diagrams and raw data to your calculations and your analysis of limitations, is designed to prove a different critical part of your competence as a technician. And for every single point, precision is the standard.
So that brings your induction to a close. But it also leaves you with the big question you'll face every single day of your career. See, it's one thing to build a circuit that works. The real challenge, and your core responsibility, is figuring out how to account for all those tiny imperfections that make the difference between a working device and a truly reliable, life-saving one.